Thank you, Marcia. Thank you for inviting me and give this webinar. Welcome everyone to this webinar where I will be presenting parametric design in Diana. My name is Robin van der Haven and I'm working for 4 years now as structural engineer at Royal HaskoningDHV. And I'm also part of the hackathon team where I develop tools for our engineering work. So today I would like to discuss several things. First, I would like to start with a small example, which was my first project at Royal HaskoningDHV. Then I would like to talk about digital engineering and see how parametric design is part of it. And then in the end, I would like to show some examples. So 4 years ago, I started in a project which is called VIIA. And this project is about earthquakes in the northern part of the Netherlands. And there are lots of buildings which are made of masonry. And masonry is not that much used in earthquake areas. So there was research needed to see what is the capacity of masonry. And to do this, I did analysis in Diana, doing nonlinear time history analysis to see what is the capacity of the masonry wall, and then included nonlinear material behavior of the wall. And to see what is the influence of different parameters, I did a parametric study, changing the height, the thickness, the type of masonry, and also I applied different subsoils to see what is the influence on the capacity of the wall. And I did hundreds of analysis and also processed the data to see what are the results and how parameters are related to the capacity. And by then, 4 years ago, Diana released their the Diana 10 version, which included a Python console, which allowed me to interact with Diana interactively. And therefore, I could use Python to do this work and to do a parametric study. So it helped me a lot to do this study. So that was 4 years ago, and now I'm still working on parametric design and also other topics and developing tools at Royal HaskoningDHV. And this is all part of what I call digital engineering. I would like to talk about you on digital engineering, which and parametric design is, I believe, part of digital engineering. And I would like to see how parametric design is related to digital engineering and what other topics are related to parametric design and how they relate to each other, and also how they can boost each other. Because I think digital engineering is important because excellent designs arise in an iterative process in which multiple disciplines work closely together. And I think we need digital tooling to achieve this, because what we see now in the current workflow is that the iterative design process is disrupted. For example, when there's a design change, for example, then we have to do rework, and that's time consuming and also error prone. And sometimes we try to use tools, but these are not developed or integrated in the process. And then, this is also troublesome. So I think I believe that digital engineering can solve this problem and help us to make better designs and also have a better quality. So if we look to digital engineering, I think we can distinguish 4 categories which are part of digital engineering, and parametric design is one of them. And the others are interoperability, automated engineering, and generative design. And I will talk about all 4 of these and show how they are related, how they also may overlap each other a little bit, and also how they can boost each other. So first of all, what is parametric design? I start with this simple example to get an idea of what we're talking about. And then the basis parametric design is creating relations and describing relations. For example, here we have a line and we have 2 points, and we describe a relation between these 2 points, that there is a line in between. And these relations can be about any entities. Now there are 2 points and a line, but we can also have multiple points and make a polyline or anything else. Another example is this box or this cube. At the left side, you see the aesthetic model, and that's actually sort of the conventional way of working, where we have just a static model, and if we want to change something, we have to change it in CAD modeling software. Yeah, that's the current way. And then the right-hand side, you see a parametric model, which is a dynamic model. And what we do in parametric design is that we not modeling the box itself, but we're describing the relations. So we're describing how the input parameters X, Y, and Z are related to this box and how it can create this box. And what's interesting is that there's also an output parameter, the volume, and it is evaluated in every step. This helps us to, for example, evaluate cost or mass or that kind of things of a model. So if we want to do parametric design, there's also software to do this. The previous examples were from Grasshopper, which is a visual programming language for Rhino. And within Grasshopper, you can also do FEM analysis using a plugin called Karamba. Then you also have Dynamo, which is a visual programming language for Revit, which is a BIM program. And of course, you can use programming languages to do parametric design, for example, in Dynamo with Python. You also have Python for programming frameworks, for example, PyPy, which is a framework for Python, where you can do parametric design. So I'll show all of them briefly. So the first one is Rhino and Grasshopper, and in Rhino you can model geometry, and it's especially good with modeling complex geometries. And it's also used a lot for rendering and also for virtual reality. And what's nice is that you can interact with it using Grasshopper. And Grasshopper is a visual programming language, and you can link boxes with each other with wires, and in this way you make these relations to create your parametric design. And there are a lot of plugins to, for example, do FEM analysis, but also other analysis you can do with Grasshopper and the plugins. And here you see 2 models which are created with Karamba, and you can do structural or FEM analysis, but also, for example, do cross-section optimization. And every time your parametric model updates, the FEM analysis is also updated. Here we see an example of how this works in Grasshopper. So we see a Grasshopper script for a cable stayed bridge, where we can change with the parameters the shape of the bridge and the number of cables. And then we use Karamba to determine the structural safety, and then we can use an optimization algorithm, Galapagos, which is also in Grasshopper, which can find the optimum shape for you with the minimum kilograms. So this gives hopefully a bit of insight in how you can use this program to generate a model, but also evaluate and optimize it. Then we have Dynamo. Here you see an example of Dynamo where we used it to generate the Revit model of the Feyenoord roof stadium, or the roof of the Feyenoord stadium. And here you also see that Dynamo is a visual programming language where you can connect boxes with each other using wires, and in this way create relations. And here you see that you can use it to generate a BIM model in Revit, but also adapt and manipulate it. Then the last example is in PyPy. Here you see that you can make a Python script in PowerPy, and when you run the script, the user interface of PowerPy will pop up, and then you will see your 3D model. This is a roof for a train station, and when you change, for example, the size, then the size of the roof is increased, and you see that it can be reduced again, and also, for example, the height of beams can be increased or reduced. This was part of a hackathon where we tried to make this plugin or this tool in 2 days, and we also create a writer to Diana, which writes a dot file based on the current model, and then does an analysis. And every time we change a parameter, then an analysis is triggered, and the unity checks are updated. And in this way, you can sort of iteratively check what kind of parameters are needed to have a good structure. All right, so that was parametric design. And now we go to the next topic, interoperability. And this is all about connecting data between different disciplines, but also within a discipline. And at first, what I saw at Royal HaskoningDHV, and I can imagine it happens also in other companies, is that we try to connect specific software with another software package. And then you get all these direct lines from one discipline to another. And at some point, this becomes chaotic and also not maintainable. So what we do to help us with interoperability, we have a platform called Data Fuser. And what it does is that this functions as a central point to communicate data. And what you see at the right is that when the number of systems increases, the number of connections is not increasing exponentially, but linear. So that's a big improvement in terms of maintainability. So it helps us to connect data, but also within such a discipline, we create software to help us to connect to Data Fuser and to create our models. So now we're going to look into FEM. We've created a FEM package in Python where we can create and change FEM models, but we can also share FEM data. For example, if we want to go from Karamba to SIA or Diana, we can do this with the RHDHV FEM package. We can send the data to our own format and then unpack it in one of the other programs. And that helps us to do the specific analysis in the program which is suited for the job. And also it's a toolbox for engineering. For example, unity checks can be carried out, or specific materials can be generated and assigned to a model. So this is a handy package to work with and to easily make FEM models. And now we're going to look to an example where we go from Karamba to Diana. So here we see the Grasshopper script, and at the left side you have input parameters. Then in the middle, a lot of stuff happens to create the model. And now we're going to look to the model. It's at the right side in the viewer. And you can see that's a truss structure with a load and connections and supports and all the data to have a FEM model. And then here we have our input values, and we can change the span and the ratio to adjust the model. And what we now are going to do is that we're going to create a JSON file which will contain all the structural data of this model. And we do this with the nodes you see here in the screen. And at the right side, the file is created. Then here we have the Python file to actually start a project. This is part of the FEM package. And what we first do is start a project. Then we're reading this JSON file, which is created in Karamba. And then we create a model. And in this case, we want to go to Diana. So we specify Diana. And what we do is that we then open Diana and run this script in the Diana console. and this will take some time. All the geometry, all the shapes are created, all the materials and supports and loads, and they are all assigned. And now we have a Dynamo model which we can use to do our calculation. And of course, we can update the Grasshopper script. So for example, here you see the model again, and we can, for example, change the span to something smaller or something larger, and we can change the ratio. And now we have our new model. Automatically a JSON is created, so we can again run the script, and now you will see that a new model is created. So this is basically how it works. And this is just for a small example, but we, for example, do this also for larger structures, which is very beneficial for us to do our work as a structural engineer and to do specific analysis in Dynamo and other analysis we do in Karamba or in another program. So that was interoperability, and this next topic is about automated engineering. And this is about doing engineering work in an automated way. You can think of, for example, doing a unity check for a beam. This can be fully automated with the script, and then we talk about automated engineering. And the example which I'm going to show here is about modeling a soil block, and this is needed for doing earthquake analysis. And usually this took us almost a week in the VIIA project, because we have to determine quite a lot of properties for the different soil layers, and also the modeling itself took some time. And in the end, we made a script to do the work for us. So the geotechnical engineer supplied us with the input data. This was read by this script, and then all the properties for each layer in the soil are determined and is modeled and also assigned to the different layers. And here you can see how it works. Step by step, all the layers are made, and also the supports and the springs are created with the correct stiffness. And now we have our soil block. It's now meshed. I will go to the end. Then you can see that it's a meshed soil block, which can be used in our analysis. So this is a good example of automated engineering, where something which took us a week can now be done in less than an hour. And the last item is generative design. And this is a topic where actually all previous categories come together. It's partly parametric design, but also automated engineering and also interoperability. And generative design is about generating the designs based, for example, on your parametric model, and then evaluate them and come up in the end with the best design using an algorithm. And there are a lot of them, and one of them is evolutionary algorithms. And to explain how this sort of works is that you can generate a couple of designs based on your parametric model, and then evaluate these designs, and then choose to throw away the bad ones, and the ones who perform well, you keep them. And then in the next step, you create new models based on the good performing ones, and you have a new set which will generate this new input, and then you can do this multiple times, and in the end you will have a good design. And you can think of an example like this, where you have a solid and we are removing material to come up with a bridge design. At Royal HaskoningDHV, we are currently working on 3D printing. This was one of the tryouts to see how it works with the software, and also when printing it, what will be the result. And this was the result of our first tryout. So now let's go to the examples. I will show 3 examples, and all of them contain a little bit of parametric design, but also of the other topics of digital engineering. And the first one is about image recognition. The second one is about LNG tanks, and the third one is about the Fine Arts Stadium. So the image recognition tool is used also in the VIIA project, because we have to assess a lot of buildings and we have to model quite a lot of buildings, and we want to do this in a more efficient way. So we came up with a user-friendly tool to create 3D FEM models from 2D drawings using image recognition. And what we do is that we draw lines on plan views, and based on these lines we can generate such a model. And we do this by evaluating these lines, and then structural shapes are created based on the contours, and also the color indicates which type of material it is. And we have different drawings, for example, one for foundation, one for the walls, for beams, and for roofs. And based on the colors, the right material and shape is created. And to help people work with this tool, we have created a user interface. As first step, you can import your drawings, your lines, as you see at the left. And then you can link the colors to different kind of materials. And then you can run a Python script. And in the end, you have your Dynamo model, which you can use for your assessment of the building. So in this way, we could model buildings in a much faster way. Then the next example is LNG tanks. In the last years, we have engineered a lot of them. And also for this, we used scripting to automate this process. This is from a while ago. When we started with the hackathon team, this was one of the first projects. And what we do is we have an Excel sheet with the input data. And this input data serves as input for Dynamo as well as for Python for Diana. And first you see Dynamo, and in the Dynamo player, one of the scripts is selected and the input Excel is selected, and now you see that the model is created and also the drawings are created. And also we can use the same Excel to serve as an input for our Python script. And here you see that the LNG tank is created in Diana, and all materials and geometries are assigned, and also loads and load combinations and supports. And analysis can be done, and now we can assess the LNG tank and come up with a good design. So here you see that it helps us to do our work in a more efficient way, but also to have more quality, because we use the same input for our BIM model as well as for the calculation model. And in this way, we're sure that both use the same data. Then the last example, the new Fine Arts Stadium. This is the project I'm currently working on. And in this project, we use parametric design right from the start, because it's a complex design project. And we foresaw that there would be changes in the design, and we would like to respond on these changes in an efficient way. So we want to work with the central model. And also it's an ambitious project where there's lots of opportunities to optimize the design. So let's see how we approach this design of this new stadium. We started defining reference surfaces together with the architect. So for example, for the tier layout at the front, we defined that these are reference surfaces, but also the bowl for the facade and also the roof. And the different levels were indicated. And then in the design, they want to have sort of floating bowl. So they should be supported by cores, which were over here. And these reference lines plus the cores and the levels give reference points. And this is a point cloud which results in this model. And this model was used as our coordination model. So if there's a change in design, then for example, the roof opening becomes bigger or the height increases, then all these changes were done in this model. And this model serves as an input for the other models. And we use Data Fuser to send this model to other models of other disciplines. So we have a structural model, an MEP model, a CFD model for wind hindrance, and a BIM model in Revit. So here you see the structural design of the roof. And in this process, we looked into two options, an outrigger option and an option where we have simply supported beams or trusses. And what we did during the design process is compare both options constantly. So every time something changes, for example, the roof opening became larger or smaller, or the structural height increases, then we could compare both options and see how well they performed. Because we used Karamba, and with Karamba, you can do FEM analysis, but you can also do a cross-section optimization. So based on the model, you can ask to Karamba, what is the optimum cross-section and what is then the total weight of my structure? And this gives an indication of the cost for the structure. So in this way, we could compare both options and also advise others in what to do and what influence design decision has on the total cost. Another aspect is that we looked into building installations. Here you see the air ventilation systems. They are positioned on the grid, and also here there's a parametric design applied to position them and also change them if they also respond to the changes in the coordination model. And here you see the CFD model, which we used to analyze wind hindrance around the stadium and in the stadium. And to make this CFD model, we also used this coordination model as a basis to come up with a suitable model for this analysis. And at first we thought we could do 2 or 3 analyses during the process, because normally it would take quite some time to model such a CFD model. But now we could constantly update this model of the stadium, and we could do a lot of more tests with the CFD model to see what is the influence on wind, and in this way we could do our work in a better way. In the end, we also did a wind tunnel test, and this model you see here is 3D printed, and it's based on the other models we made in the design process. And also here we looked into the results of the wind pressures, and also checked these results with the CFD results, and they matched quite well. Then we also generated our BIM model of the stadium. So we used Dynamo to generate all the elements in the stadium based on the structural models in Karamba. So all the geometry you see at the right is all generated. So none of it is clicked by a Revit modeler. Another thing which we used was virtual reality. Together with our client and the architect, we discussed the design a lot of times using virtual reality. And one of the examples is that, for example, we had a discussion on the height of this main truss you see over here, and what would be the impact in the stadium if you would higher or lower this main truss. So we put a VR bureau lens on on the different on the persons, and they could see the impact of what it would do with the view in the stadium. So another thing what we did is optimize sightlines. You can imagine that if you change the inclination of this stair, that you can see the pitch better or worse, depending on how well you can look over the person who's sitting in front of you. And this is measured with the C value, and the absolute minimum is 60, and 90 was the minimum we want to achieve with the Feyenoord Stadium, and that was the goal from our client. So to do this, we created a script to generate this tier layout, but also evaluate the C value on any position in the stadium, and then we could change the tier layout to see if the if it improves or not. And here you can see that we changed the tiers, the inclination of the tiers and the position, and then in the end you have all positions in the stadium have a C value higher than 90, and this results in a very nice view within the stadium on the pitch. Another thing is that we optimized weight, so not only for the view but also for in terms of performance with regard to the number of kilograms steel. We looked into different heights. So for example, 12 meters resulted in a total weight of 4,600 tons. Then 14 meters results in a mass of 4,000 tons. And then 16 meters results in a total of approximately 3,700 tons. And here you can see how that works in Karamba and Grasshopper. So at here you see 12 meters and the weight is 4.6, and now we change it to 40 meters, and then the design is optimized and you see the new optimized weight, and at the right side you see the result, and then we increase the height to 60 meters. And then you will see that the optimized mass decreases even further, and then we can also look to the result, and then we see that the truss height increased again. So and then the question is, what is the ideal height? And that's something you have to discuss with your client and also the architect. And this is these toolings like Karamba and other parametric design tools helps us to make informed decisions and to see what is a good choice to make in designs. So this was my webinar about parametric design. I hope you enjoyed it, and I'm curious if there are any questions on the things I presented. Thank you.